All right, let's continue with section 2.2, limits of a function. The example we just completed was the limit as x approaches 1 of x minus 1 over x squared minus 1. That was equal to 0.5. That's a rational function. Maybe you remember graphing those back in Math 171. It has a hole when x is equal to 1, and the location of that hole is at 1/2. So you could create a new function, we'll name it g, that looks exactly like f, x minus 1 over x squared minus 1, except at the point when x is equal to 2 and when x is equal to 1, and when x is equal to 1, g of x is equal to 2. So it jumps right up here. This function is defined when x is equal to 1, whereas f was not defined when x is equal to 1. But they have the exact same limit as x approaches 1. Now let's look at another example. And we're just going to do the same process we did, but we're going to use Desmos instead of our calculator, so you'll have another tool to use for calculating these. Now here's my Desmos. First thing I will do is type my function in, f of x. I wrote it on my page so I didn't have to try to memorize it. Squirt, and of course I use x's instead of t's, plus 9 minus 3, highlight all that, divided by x squared. Now let's zoom in a bit. We want to know what's happening when my x's are getting closer and closer to 0, and we can see it's not defined when x is equal to 0. We can eyeball this picture here and get a pretty good idea just from the graph what is going on. But we can also use a table here in Desmos. We have x1, and I want f of x. And pull your keyboard up here. There's your subscript, x1. So let's think about numbers that are close to 0 but a little bit smaller, like negative 0.1, negative 0.01, negative 0.001, negative 0.0001, and it's Desmos. We can get as close as we want to. Negative 0.00001, and I'm going to go back up here and give it its negative sign that I missed. Get rid of that one. Okay. And then if we put in 0, it's undefined. But we can look at numbers that are a little bit bigger than 0. 1, 0.0001, 0.001, 0.1. And again, we can see that the numbers are getting closer and closer to 1.67. Yes, I had left my decimal points out. Now you can see they're getting closer and closer to 1.67. Awesome. So we can use Desmos, we can use our calculator, and the advantage of Desmos is you get to see a nice picture of it. We can zoom in and watch as the data points get closer and closer to 1.67 on either side. Now let's go back to our PowerPoint There's the pretty picture, and that happens to be equal to 1/6. Example 6 introduces us to a function called the Heaviside function. It's named after a person named Heaviside. I thought it was because it looks like this side is heavier than that side, but no, there's really Oliver Heaviside. It's used to describe whether a current is off or on, and it's turned on at time 0. So it's off until time 0, and then it's turned on. It can be described as a piecewise function. It's equal to 0 if t is less than 0. It's equal to 1 if t is greater than or equal to 0. As t approaches 0 from the left, we get closer and closer to 0. As t approaches 0 from the right, our function, our outputs, are closer and closer to 1. So the limit as t approaches 0 does not exist. Which brings us to the need for one-sided limits. So if we approach the 0 from the left for the Heaviside function, our outputs approach 0. If we approach 0 from the right, our Heaviside function gets closer and closer to 1. And that's our notation, is the little negative sign next to 0 means we're approaching from numbers smaller than 0. The plus sign means we're approaching 0, numbers that are bigger than 0. That just explains the notation to you. The definition looks almost exactly like the definition for a regular limit, except we require x to be less than a if we're approaching from the left, and we require x to be greater than if we're approaching from the right. Now, comparing definition 1, the definition of a limit, with the definitions of one-sided limits, you can see that the limit is equal to a certain number if and only if the left-hand limit and the right-hand limit are both equal to that same number. So if the left-hand limit is different from the right-hand limit, then the limit doesn't exist. It only exists if the left and the right-hand limits are the same. We'll do some examples of this in the next video.